Hi everyone, I'm very glad to be here to present our research work titled The Impacts of Item Features and User Characteristics on Users' Perceived Serendipity or Recommendations. I am Ningxia Wang from Hong Kong Baptist University, and this work was done by me, my supervisor Dr. Lin Chen, and Yuhua Yang from Alibaba Group. So the rapid development and popularization of internet and mobile networks have made users face an overload of information, making it difficult to choose and effectively make decisions. As a popular tool of filtering massive information and helping users making decisions, recommender systems bring huge benefits to both users and suppliers. However, traditional recommender systems have mainly aimed to maximize the accuracy of item prediction, but are likely to trap users into a filter bubble. That is, the recommendations are too similar to the user's profile that stops users from exploring different items. Given this limitation, many beyond accuracy metrics have been concerned, such like novelty, diversity, and today's topic, serendipity. The original definition of serendipity is to make discoveries by accident and the sagacity of things which users were not impressed for. In recommender systems, it refers to the pleasant surprise to the user. Our previous work verified the relationships among diversity, novelty, and serendipity. Diversity and novelty can lead to unexpectedness, while novelty and unexpectedness affect serendipity directly. What's more, increased serendipity can significantly lead to higher user satisfaction with the recommendation. But because users' perceived serendipity involves their positively emotional responses, which is very subjective, so it is difficult to quantify serendipity offline. The basic idea behind existing serendipity-oriented recommender systems is either from the item's perspective or from the user's perspective. So first, most all related works capture item features that may satisfy users' needs for pleasant surprises. Do it all revised matrix factorization by adding the item popularity components, based on the assumption that less popular items may be surprising and therefore be more serendipitous. Zheng et al. Combined item popularity and item dissimilarity to define unexpectedness, based on the assumption that larger dissimilarity to the user profile can be more unexpected. Besides typical distance metrics like cosine and Jacquard distance, Nakazuzi et al. Proposed the class distance based on item taxonomy. And what's more, Kawamai proposed the estimated purchase time to reduce the time cost of the user finding the item. Shorter predict time are expected to be more serendipitous. Zhou et al. Considered how early relevantly the user accessed the item. Earlier access time is expected to be more serendipitous. Some other works considered user characteristics. Menk et al. Obtained user curiosity and level of education from social network information. They applied and verified that users with more curiosity or higher level education prefer less popular recommendations. One more user characteristic is personnel innovator probability. Innovators refers to consumers who are more sensitive to new items and purchase them in advance, which may not be noticed by the followers. So items recently purchased by them are more surprising to their followers. However, to the best of our knowledge, little work stems from end users' perspective to study and verify the actual impacts of item features or user characteristics on perceived serendipity, which may lead to the impairment of existing serendipity-oriented recommender systems' applicability. So, in this work, we are engaged in answering the following three questions. First, what item features can influence users' perceived serendipity? Second, what user characteristics can affect their perceived serendipity? And furthermore, what would they interact with item features? And third, what inspirations can this work bring to the design of serendipity-oriented recommender systems? To answer these questions, we conducted a large-scale user survey on a popular e-commerce platform that is Mobile Taobao in China. Participants first answered their age and gender, then filled out two psychological quizzes about their curiosity and big file personality, and finally gave the immediate feedback on their recommendations serendipity. For each user, we obtained his or her click and purchase data in the past 3 months. Then, following the pre-cleaning process in this figure, we filtered out missing data and outliers. There are finally 11,383 users records named. Here are statistics of users' answers and user profiles. Results of normality tests show that our data is not normally distributed. So subsequently, we will use non-parametric statistical methods. Besides the collaborative information in the user profiles, a hierarchical item classification was obtained from Mobile Taobao. Overall, there are 5 levels or item category labels. Each item's category set is actually a category path from top-level category to leaf category. For example, the category path or trousers item is from clothes to women's clothing and ends at the leaf category trousers. Now we come to the introduce all item features and user characteristics investigated in this work. We divided all item features into numerical item features and categorical item features. For numerical item features, we invoked one non-personalized item feature, that is item's popularity, which is independent of user's profile. Personalized item features reveal the relationship between the current recommendation and items in the target user's profile. Time difference is how many days from the recommendation to the latest item in the user's profile that belongs to the same category. For example, one user received a recommendation from brewed oatmeal. Based on the recommendation time and the last time she or he clicked brewed oatmeal, the time difference is 16.94 days. Category difference varies at which category level the 2 items differ. For example, one item belongs to the leaf category work uniform and another one belongs to student's uniform. Following the category path from top to leaf, there are 3 overlapping category labels. The category difference is 6 minus 3 and equals to 3. Taxonomic distance is actually the class distance proposed by Nakazuzi et al., which is the minimal hops between 2 leaf categories. For example, the taxonomic distance between work uniform and student uniform is 2. What's more, based on the methods of mapping pairwise item distances to the distance between the target item and the user's profile, we have 3 variations for both category difference and taxonomic distance, that is recent, average, and minimal. Based on Taobao's item taxonomy, each item has top level, second level, and leaf category. So we use them as 3 categorical item features with different granularity. What's more, we selected 2 product classifications commonly used in marketing and economics. The first one is SDC classification, based on how the user evaluates the product. Products belong to one of the 3 types: search, experience, and credence. Another one is for consumer product types, that is convenience, shopping, specialty, and unsought. As for user characteristics, we evolved both users' demographical characteristics, including users' age and gender, and psychological characteristics, including curiosity and Big Five personality traits. The reason why we investigate Big Five is that Cashdan et al.'s work explores the correlationships between curiosity and personality. But till now, little work has made good use of user personality to enhance serendipity. Now we set forth our results in the response to the 3 research questions. For the impacts of item features on users' perceived serendipity, the negative correlation indicates less popular items are more likely to be perceived as serendipitous. For personalized item features, we tested the significance of feature difference between high and low serendipity group. Results of Mann-Whitney test show that smaller time difference, smaller category difference, and shorter taxonomic distance expect its average version can lead to a higher perceived serendipity. What's more, besides the 3-month profile, we extracted users' past 15 days historical data. Comparison shows that the shorter-term user profile is enough to distinguish users' perceived serendipity degree. And the significances of item features on click-based and purchase-based profiles show that Item features perform better when using click profile. As in this table, some features are weakly significant or non-significant when using purchase profile. For categorical features, we conducted association rules mining to discover rules in this format, meaning that if a user ever purchased items belonging to some categories in the past 15 days, there is a high probability that she or he will pursue an item from the category X with high or low serendipity. Here, click behaviors and long-term profile-based results are too trivial to highlight interesting results. Finally, we share 4 interesting rules, one rule for each categorical features as follows. For example, the rule obtained on top-level category indicates that users who ever purchase products from small appliances and jewelry or watches or eyewear categories tend to pursue the recommendation from category clothes with low serendipity. As for user characteristics, we found that high-age users and male users are easier to feel serendipitous. The reason why young females are harder to be surprised, we think may be that they are more familiar with the online shopping environment due to frequent browsing and purchasing experience. In addition, our results verify that users with high curiosity, openness to experience, conscientiousness, extroversion, or neuroticism are more likely to give a higher score on the recommendation serendipity. But agreeableness affects users' perceived serendipity in the opposite way. To figure out the interaction effects between the 20 variations or item features and the 8 user characteristics, we conducted 160 binary logistic regression. There are 5 variations or item features whose impacts on serendipity are not influenced by user characteristics. For the rest, young users are more sensitive to items' popularity, and the 2 variations or category difference have greater impacts on users' perceived serendipity for users with low curiosity, openness, extroversion, and neuroticism. So, now that we have these findings, what inspirations can be drawn from this work to promote serendipity-oriented recommended systems? Firstly, typical accuracy-oriented systems can be enhanced by importing item features such as taxonomic distance. Secondly, for users with different characteristics, the recommendation strategies should vary. For example, now that highly curious users are easier to feel serendipitous, the surprise level of recommendations can be higher, with few concern about that being irrelevant may lead to negative feelings. Thirdly, based on the interaction effects, we can adjust the role of a certain item features in consideration of user characteristics, such as set a lower weight for the category difference for new neuroticism users. In conclusion, in this work, we find that some item features lead to higher perceived serendipity by users. Also, for categorical item features, we mined several association rules which are helpful to understand user purchase patterns. For user characteristics, we find that higher age users, males, and users with higher curiosity and 4 of the Big 5 personality traits are easier to feel serendipitous. Finally, we identified the significant interaction effects between the item features and user characteristics, which inspires users to conduct comprehensive considerations so as to more efficiently improve performance. In future, we are interested in assessing users' perceived serendipity for a list of recommendations rather than single item. We will consider other product classifications like durability and intangibility. Also, more item features will be investigated, such like the combination of temporal feature and category distance. We will also validate the generalization of our findings on other domains like movie recommendation. We will also validate the generalizability of our findings on other domains like movie recommendation, and also implement and evaluate the derived design implications in a concrete recommender system. By the way, we release the survey data publicly online. Interested researchers can follow our work or conduct related studies on it. Here is the GitHub link for your reference. That's all of my presentation. Thank you for your kind attention, and if you have any questions, please feel free to contact us.